Hello everyone, welcome to this video on load flow analysis. In this video, we shall learn load flow by decoupled method, and this is our learning outcome number 4. Now here this the decoupled method, this technique of performing load flow is not a different method, but it is simply an extension of Newton-Raphson method. So let us understand how this method, decoupled method, has been evolved from the Newton-Raphson method. So let us first understand the load flow model of Newton-Raphson. So this is the Newton-Raphson load flow model that already we have derived. So let us understand each of the term here and what that indicates. Here, delta P and delta Q, this is the power mismatch vector. H, this is the Jacobian matrix, H, N, J, L, they are the submatrices, and altogether that makes the Jacobian matrix, and this is the correction vector for phase angle and the voltage. Now let us here, the point to be noted here, let us understand what is this H, N, J and L. So H here, it is the derivative of P with respect to delta, and N, it is the derivative of active power with respect to V. And what is J? J is the derivative of Q with respect to delta, and L is the derivative of Q with respect to voltage. Now there is a very important uh, characteristic in the power system which we use to modify this NRLF model so as to get the decoupled method. So what is that characteristic? The important characteristic of the power system. The first characteristic is that the active power and the phase angle, they are strongly coupled. Let's understand this. So here you can see that I said active power and delta, they are strongly coupled. Strongly coupled in the sense that for any unit change in the phase angle, there will be a substantial amount of change in the active power, and hence there will be the existence of the elements of H submatrices. Now on another hand, P and the active power P and the voltage magnitude V are loosely coupled. So what it says here, you can see for any unit change in the voltage, there will not be much change in the active power in the system. And because of that, the element of these submatrices can be assumed as 0. So now we are assuming these to be 0. This is because of this characteristic. The characteristic says that P and delta, they are strongly coupled, and P and V are loosely coupled. Let us understand it with an understanding with the transmission line power flow. Suppose this is bus number 1. We have a voltage V1 and a phase angle be delta 1. Let this be second bus. Let the voltage be V2 and the phase angle be delta 2. And now let us say this is the active power from here to P1, P1 to 2. Now this active power P12 is strongly related to delta 1 minus delta 2. It is directly, means what, if there is a small change in the phase angle, then there will be substantial change in the active power flow. But if there is a change in the voltage, V1 minus V2 is the potential difference, and if there is any change in the voltage, then active power flow will not have any change. The active power flow will not change if there is a change in the voltage. So it is called as loosely coupled. And because of this characteristic, these submatrices n we can assume 0. Then let us take one more characteristic. Here the active power flow Q and the voltage, they are strongly coupled. So as already I have seen, I have shown here that J, that is J, it is there. Q and here I was telling that Q and V are strongly coupled. Means what? If there is a small change in the voltage, then there is a substantial change in the active power flow. Okay, suppose I say that there is active power flow of Q1 2 from 1 to 2, then even a small change in the voltage, suppose V1 minus V2 is the potential difference, and if there is a small change in the voltage difference, then Q1 2 will change. There will be a very enormous change in the reactive power flow, and then we say that Q and V are strongly coupled. So there will be an existence of elements of the submatrices L. But whereas the reactive power and delta, they will be loosely coupled, and hence we can assume the elements of the submatrices J to be 0. So with these characteristic of the power system, this NRLF model can be modified to this. We can decouple that one matrices into two matrices. So this is one matrices. Here in this we have assumed n equal to 0, and there is another matrix where J submatrix is assumed to be 0. So we have decoupled the NRLF model into two models. These equations are called as decoupled load flow model. This is called as decoupled load flow model, and it is used for performing load flow. Now, what is the advantage of decoupling the NRLF model into two models? The advantage is that the computation, there will be a reduction in the computational time, or it will not be not time consuming. But the problem is that this method is computational time is less, but it will take more iterations. So in this we have learned this decoupled load flow how to perform load flow by decoupled method. In the next video, we shall go to fast decoupled method. So in this video, up to this only. Thank you very much.